So it's Peter Vetter from Nokia. He's the president of Bell Labs Core Research in the US, and Peter is bringing a guest, and the guest is Takehiro Nakamura. So Nakamura-san is the senior vice president for NTT DOCOMO. So I thank Peter for being here and for inviting Takehiro, and Takehiro for accepting to be here as well. Guys, the floor is yours. Thank you very much.
Thanks, Luis, for this kind introduction. And yes, we are going to innovate a bit in terms of giving a keynote because we wanted to give a bit of a dual perspective on the future of 6G. From a service provider perspective, what are the use cases, what is the deployment, and from a system vendor perspective, what are the new technologies that we see happen for the 6G era. So I'm also very pleased to be in the same keynote session as Ted Rappaport. I can say that NYU and NTT DOCOMO outside of Europe are our most important 6G research partners. So we titled our talk, 6G Getting into the Next Gear. The main point will be that we're getting out of that exploration phase of research, and we are seeing tangible first proof points of things that can be done for 6G, and we need to start thinking of the systematization and getting ready also for the pre-standardization efforts. It's already the 5th 6G summit. I still remember the very first 6G summit when Professor Matti Latva-Aho has put this giant 6G sculpture on stage. And that was really the first time that we at an event started talking about the 6G vision, and both Nakamura-san and myself, we were speakers at that event. Since then, 4 years later, a lot of things have happened. We had a first round of research projects, European-funded research projects, including the flagship project HEXA-X. In the European context, more than 20 initiatives were taken by over 150 organizations. In the meantime, the SNS, the Smart Network Services Joint Undertaking, has been created, and there is a commitment for 1.8 billion private and public funding for the next 5 years in 6G research. 35 projects already accepted in that, and including there also the second phase of HEXA-X, the flagship project. And then also if you look in the media, more than 2,000 articles and other media, video blogs and such have been published. And then important for the research community, if you do the search on IEEE Explore, more than 6,000 research papers on 6G. So lots of things have happened already in 6G, and we're really getting into that next gear. When preparing this talk, I said, let me look back to what I said in Levy. And one of the main points, I made a reflection of the generation every decade. And every generation is defined by three defining attributes. There must be a defining new application. There must be a defining new radio technology, aiming for higher and higher frequency bands with wider and wider bands, as Ted so eloquently explained. And then there must be a defining new platform technology that enables the new applications as well as the new networks. And the icons speak for themselves. I don't need to talk through all of them, but just to anchor a bit that thinking for 5G, that defining application has been industrial automation. The defining new radio technology has been 5G millimeter wave. In the meantime, we have seen that most of the deployment happens with massive MIMO technology in the midband. So there's a bit of a reflection and lesson learned that we need to take into account for going forward to 6G. And then the defining platform has been distributed compute in distributed cloud to enable low latency applications as well as enabling cloudified network functions. So in 2019, we already started defining what is the application then for 6G. And we recognize this importance of the fusion of digital and physical worlds already at that time. In terms of new radio technology, we started thinking of, hey, let's go to even higher frequency bands, subterahertz, where there's wider bands available. And then the defining platform for compute and also for new network designs, AI. So one more thing before I get there. Every generation in the European context is also defined by a defining flagship project. The European research programs have been very foundational in laying the groundwork for every generation. And you can point to a flagship project, say, for instance, for 4G, that was the Winner project, and there was an overarching umbrella organization, the Wireless World Initiative. In 5G, we had METIS as the flagship project, and the overarching umbrella was the 5G private-public partnership. In 2019, we started defining and creating the consortium for the, we have the animation there. This is how it works, yes. In 2019, we started the creation of the HEXA-X consortium as the flagship project for 6G. Now, 4 years later, HEXA-X is coming to an end and starts its second phase. Let's have a fresh look at these. So the defining application, we see the confirmation of that digital physical fusion. Metaverse became a thing in the meantime. We become a bit more cautious on the excitement about subterahertz, all credit to academic research like Ted Rappaport, but lesson learned. Mid-band deployments is the dominant thing in 5G. There's another very important band that we need to look at, that is the 7 to 15 gigahertz, the upper mid-band. And then third, in terms of defining compute platform, yes, AI very much confirmed what it can do for the radio interface as well as what it can do for the way we network. And we're going to structure our keynote according to these three big aspects.
Okay, so from here, I'd like to explain the 60 applications, especially for the digital physical fusion. Next. Yeah, actually, digital physical fusion is very, very important, even for now, to create a new business for us, for operators. But that will be more essential in the future. And also, we believe that digital physical fusion can augment the human possibilities enabled by the metaverses. And we have three kinds of metaverse, we think. And industrial metaverse, enterprise metaverse, and the consumer metaverse. And the industrial metaverse is OT-centric, and maybe industrial automation focus, and also OT, or operation result-driven. Enterprise metaverse, this is IT-centric, of course, and that can be enterprise business-driven, and that will be boosted by the evolved XR devices and immersive virtual space application, and so on. And the consumer metaverse, that is, of course, consumer appeal-driven. And also, maybe excellent XR devices can boost this growth. Okay. And this slide shows growth of the metaverse segments, three metaverse segments. Clearly, we can see that significant revenue potentials in all of these three metaverses. But growth speed is different. It seems that the enterprise metaverse and the consumer metaverse, the growth speed is a little bit slow. We need to wait for the excellent XR devices and nice applications for several years to boost the growth of these metaverse. On the other hand, industrial metaverse, the growth speed is faster than the others, thanks to the early traction of the industrial automation solution applicability. And yeah, next please. And I think that for that, the 6G infrastructure taking a very important role. And in this case, for the digital physical fusion, the huge amount of data of the physical world and the human world need to be transferred to the digital world. And then that data will be processed, analyzed by AI in the digital world, and quickly actuated to the physical world. In order to do that, our 6G infrastructure has a very, very high performance, such as the extreme high data rate and the capacity, and the extreme low latency, and the extreme high reliability. These are the further improvement of the 5G capability. And also, we need to realize by the 6G infrastructure the extreme coverage to connect the unconnected. And also extreme low energy and the cost. This is, of course, very important for the sustainable society. And also extreme massive connectivity and the sensing. The accurate sensing capability is very, very essential for the digital physical fusion in the 6G era.
Yeah, I want to pick up on that sensing capability. So indeed, to enable the synchronous update of the digital twins in the digital world with the physical world, you need massive deployment of sensing. And 6G has an opportunity for an additional sensing modality that then can be fused with other sensing modalities, and that is radio. Because we will have radio all around us for the communication, but we can use these radio signals also as a radar. So joint communication and sensing. We're not inventing the radar itself, but the key point is that we do this jointly while maintaining the quality of service of the communication system. So, and what can you do? You can do localization of humans and objects with an accuracy of tens of centimeters. You can even detect shape. You can have Doppler effect and see motion. You can also see motion of chest, breathing, heart rate, so vital signs. And you can then, using AI, deduce higher order meaning. When I see chest movement or so, oh, this must be a mammal or a human. If I see the frequency component of a rotating fan, that must be a piece of equipment there. So there's higher order meaning that we can deduce applying AI to the sensed signals. So we've built the first proof of concept using an OFDM 28 gigahertz 3GPP millimeter wave system. We took great care that we can really do that joint communication, and we have algorithmic innovations that optimize the quality of service of the communication and optimize the beamforming for maximum resolution for the sensing application. And we then have the combined intelligence. So there is on one hand the enabled millimeter wave access point, but then also additional sniffers, as you can see in this picture, and then additional offline process. It's actually real-time processing to make sense of what we see. For those people that have been at Mobile World Congress, we actually demonstrated this live at Mobile World Congress, and to create a bit of an experience, we created this giant piano along the wall, and while you were walking along the system behind that screen, that 28 millimeter wave access system sensed the location, and so you could play the tune of that piano. And to show that it is real, we actually then also blocked the millimeter wave system, and then at that moment the piano stopped playing. So it was a real live system going on. But there's more that we can do. Joint communication and sensing is not only in the radio space. As you maybe have noticed, Nokia has a new brand, a new logo, and the A in the logo actually also looks like a lambda, and that stands for wavelength as in radio, but also optical wavelengths. And the future 6G network, it's not only about the radio, it's the end-to-end network, and the optical transport network will be an essential part of the future 6G network. And also in optical fiber networks, you can apply sensing. Actually, here in Göteborg, we have a trial going on with aerial installed fiber cables. And you can use coherent optical communication systems to say phase shifts. And when you apply mechanical strain, you can see subtle differences. Subtle differences that, for instance, help us to estimate wind speeds and predict possible, if there's very heavy winds, the breakage of cables. We can also detect temperature, and that can help us localize potential fires, God forbid that they happen. Also in transoceanic systems, much longer systems, at the bottom of the sea where it's a lot quieter, we can detect wave motions of tidal waves, of tsunami waves, and start predicting the tsunamis. We can see the passing of a ship or the dropping of an anchor. So very interesting use cases that you can use from that. Also, DOCOMO, in the context of IOWN, is working and researching the capabilities of fiber in urban infrastructure to sense the traffic.
Okay, so use cases of the radio sensing. Yeah, we have already discussed so much about the variety of the use cases for the radio sensing in the 3GPP. But I showed that 4 typical use cases here. And what's one is the detection of the intruder to railway. This is very useful solution, use cases for the railway company for safe operation. And if we can detect the wild animals on the railway, maybe we can take a proper action for the emergency stop in advance. And congestion detection. This is very, very typical use cases for the radio sensing. And maybe we can use this kind of the use cases, solutions for the shop, theater, restaurant, and the event venue, and so on. And behavior health monitoring. This could be useful and essential to save human life. And local rainfall estimation. This is now very useful due to the global climate change. And in Japan, we have serious disasters due to the local rainfall, so-called guerrilla heavy rain in Japan. And yeah, if we can detect the local guerrilla heavy rain very quickly, maybe we can use that kind of information to mitigate the damage. Yeah, please. And also, we believe that we can monetize digital physical fusion by the sensing and AI. This is a high-level example of the architecture of the sensing and the AI. From the bottom, yes, maybe we can have several kinds of the sensing measures, including the joint communication and the sensing, and also sensors implemented to our network facilities. And also for the future, HAPS or NTN, maybe satellite HAPS can install the sensors or cameras. The data detected by those kind of the sensors should transfer to our operator's MEC and stored, analyzed by AI and controlled. And those kind of the data can be used for the many kind of the use cases for our business. Of course, the applications should be developed, installed to our operator's MEC, but together with the variety of the partners, so that we can develop the very excellent applications in agile manner. And of course, the applications in the internet, public cloud, should be used by cooperation with the other systems and stakeholders.
Okay, so we talked about the defining applications. Let's move to the next, the defining radio technologies. And as said, I want to talk about the 7 to 15 gigahertz as what we will call the golden band, the upper mid-band for 6G, and then also exploring what subterahertz can do for 6G. This is a well-known figure. You recognize the spectral bands for 4G and 5G that are currently used, and you see also their range. So you have the low band that really provides the wide coverage. Then you have the mid-band where we apply massive MIMO to achieve high capacity. And then you have the millimeter wave with limited coverage and small cell deployments in hotspots for extreme capacity support. And we can expect that in 6G, we will repurpose these bands also for 6G applications and allow for flexible sharing of spectrum across generations. But there's two important new bands. So there is the 7 to 15 gigahertz. And our simulations show that you can have a nearly same coverage as with the current midband in that upper midband. And that provides an excellent opportunity to provide high capacity from existing cell sites. Because lesson learned from 5G, if you can provide the capacity from existing cell sites, then that's what will be done. And then for the extreme capacity, we see a future in repurposing the millimeter wave, and then the terahertz that has even smaller capacity, yes, in small cell deployments, and we see a future there if there is additional capabilities for value creation in terms of using it for sensing with higher accuracy. So let's first look at the upper midband. And I want to start by saying that with distributed massive MIMO, you have already a first opportunity to enhance capacity. We've demonstrated that and did a technical trial with AT&T in the current midband 3.5 gigahertz. And we see that really as a stepping stone and a technology that we can then also use in 6G. But to really get to that almost same coverage, you will need many more antenna elements in your array to have the finer beamforming. It will be digital beamforming because there's a lot of angular spread that we need to deal with. So there's some considerations on hybrid beamforming and digital beamforming to find that right optimum. Physics is on our side. Half the wavelength means that in the same form factor, you can fit 4 times more antenna elements. It's mainly how do you do the processing in an energy-efficient way that will be an important challenge. And a direction, and that's why I introduced the distributed massive MIMO, also a modular approach and a distributed processing within the panel is a more energy-efficient direction and a lower complexity direction that we're looking for. Then in subterahertz, we do invest in subterahertz radio transmission and research. The earlier applications that we see, that we definitely see happen is 100 gigabit per second for wireless backhaul and front haul. An important challenge is not only low-cost RFICs at those high frequencies, but then also the packaging. The classical PCB technology with epoxy have too much of an attenuation at the frequencies that we're looking. We need new materials. We're researching radio and glass. And it's not glass as in transparent. It is really the material property that shows lower attenuation and permittivities that are more amenable for these high frequencies above 100 gigahertz. And you see here actually an antenna design, a large array antenna, and on the backside we flip chip bonded our RFICs. Also important is then research of new waveforms. We experimented over the air to really achieve to a more energy efficient signal processing and taking into account also the phase noise, for instance, that happen at those frequencies. And then as Ted Rappaport has done already quite a lot of pioneering work in that space, we need lots of data samples in different environments, urban, suburban, tree-lined streets, and what have you, and indoor, to have accurate channel models at those high frequencies. And not only for the communication, but to what we said earlier, also how do these channels behave for sensing the reflectivity of surfaces and so on. And then there's a whole set of technologies that apply to any of these frequency ranges, really, the upper midband, the millimeter wave, and the subterahertz, to enhance the coverage at a low cost. And DOCOMO and partners and Nokia and partners are looking into these different technologies. And here, for instance, we do have antenna on glass, and here it is about making the antenna invisible. Also, low-cost pinchable antenna arrays, new and fresh looks at front haul, revisit the analog over fiber, orbital angular momentum over the air, and then also repeater systems, reflectors, in reconfigurable intelligence surfaces, or also passive lenses. Okay, so I'd like to explain why we need a higher capacity in the 6G era. And this slide shows the forecast on the global mobile traffic per year.
traffic increase and also global radio capacity increase. And the left-hand side shows the increase in the traffic. As you may know, our traffic is increasing continuously by 1.2 to 1.5 times a year. And especially, we need to take care about AR, VR traffic, as shown in the purple bar. And that will be increased drastically in the future. So for the non-AR, VR traffic, green part, maybe for only that traffic, maybe we can cover the existing spectrum resources like sub-6 with the 5G technologies. That can be enough. But to cope with the AR, VR traffic that will be increased drastically in the future, we need additional frequency resources, spectrum resources around sub-7 gigahertz with the 5G advanced technologies by the 2030. But after the 2030, traffic will increase more and more, and we will need further additional spectrum resources at the 7 to 15, higher midband, with the 6G technologies to cover that. Next, please. And what kind of the use cases can be considered using the higher frequency band? Of course, the higher capacity use cases which need a higher capacity, especially for downlink, peak data rate above 100 gigabps. Maybe we can consider the variety of the use cases for the future, but one of the examples should be as you can see, the left-hand side, realistic human-to-human and the machine interaction in the healthcare and the enterprise. And in the future, we can use the very excellent AR, VR devices and also excellent metaverse solutions and also photonics and then everything. That can be used, and also we can provide a very excellent services like human-to-human, human-to-machine, and so on. And also the higher frequency band use can provide additional benefit. That is very accurate sensing with high resolution, thanks to the very shorter wavelengths. And with that, technologies maybe realize that kind of gesture recognition use cases, and also autonomous driving. That automotive industry need a very, very high resolution, high accurate sensing, positioning accuracies. So this should be a good example of the use cases. Next, please. And also uplink. And even for now, our customers need a very high performance uplink, especially for the remote control and the remote surveillance use cases. But for the future, in addition to that, as I said, the digital physical fusion world will come. And a huge amount of data need to be transferred to the digital world. The state of the physical world, for example, the city data and the factory, farm, and also vital signs of the human body need to be transferred to the digital world so that we can support the development in the industry and the well-being society.
Okay, so we arrive now after the second pillar, the defining radio technology, now the defining platform technology, AI. And staying with the radio interface, we'll see what that can do for the physical layer connectivity, AI, but then we'll also look at the importance of AI for future network architectures. Let's start with the radio interface. So you see here the classical design of a transmitter and a receiver with its respective functional blocks. And there's already a large body of research on how you can optimize these individual functional blocks like synchronization, channel estimation, equalization with machine learning. Now, at the interfaces of each of these blocks, actually information gets lost. So we realized that if we start integrating some of these blocks and treat them as a whole, more information is maintained and you get to more accurate learning principles and better performance. So we devised this deep learning receiver that not only provides better performance, but actually there's also opportunity for simplification, because you can then start thinking of reducing the total number of layers in your machine learning. Notice that you can do this already in 5G or 5G advanced. It is localized in the receiver. If you start defining a new interface, then there's lots more that you can do, because then you have a feedback loop across the transmitter and the receiver. You can optimize at the transmit side, new waveforms, self-learned waveforms. You can optimize the beamforming, and that in conjunction with transmit and receive over a newly defined air interface. And we've built it this 6G end-to-end AI system for real, with a deep transmitter and a deep receiver. Some of you may have seen it in our Nokia booth. And on the right-hand side, you see a self-learned waveform. And it's really amazing how AI comes up with an optimal constellation depending on the instantaneous channel condition. And compared to the quadrature amplitude modulation, this is much more intuitive to have these polar constellation in I and Q space. And there is an asymmetry, and if you think of it, that also makes sense, because you have more phase information, so you can get better performance in that. On that GPU-based system, we implemented a classical radio as well as an AI air interface, a native AI air interface, and we see performance improvements of up to 30% using these systems in fast-changing channels. Pedestrians is up to 18%. So there's significant improvements that we get. But there's an important challenge here, that AI processing requires quite some energy. And so in conjunction with this research, we also need to look at new ASIC technologies that lower the total energy consumption, that allow for more operations per second per watt. And some of the directions are compute in memory and analog and mixed signal compute. In our research at Bell Labs, we also look at optical computing and how you can create optical neural networks. And this is promising for inference at very high line rates. So to achieve high speed applications going really to the hundreds of gigabit speeds per second. While we use AI and trying to approach Shannon limit, it's also a good moment to pause. And Shannon at Bell Labs, he wrote that famous paper, and in the introduction, it was actually his colleague Weaver that said there's actually 3 levels of communication. There is the communication of bits and symbols. There is the communication of the meaning, the semantic communication as a second level. And then as a third level, there is, do I really achieve my goal, the effective communication? And Shannon famously said, well, that the meaning and achieving the goal, that's a human problem. The real engineering problem, that's the transmission of bits and symbols with minimal error. And that's what we did for decades. But now that the endpoints become machines, and with AI and ML, the conveying of meaning and the execution of a goal are becoming part of the engineering problem. And so there's a new area of research on semantic communication and effective communication that starts becoming important. And here's just one example to explain that concept. So the goal here is to identify people in the camera view. And how this is done today is you have, on one end, feature extraction that is then transferred over a wireless link to the other side, where you have then coding that compares that with a database to give you the identity of people. Now, today, these problems, the identification of people and the transmission over the link, are treated as separate problems, and you likely end up with a suboptimal solution in the combination of the two. And you see where this is going. If I combine the two problems, and especially in a lossy channel or a low energy constraint channel, you can get to more optimal solutions if you think of this as an effective communication problem and really thinking of the goal that you're trying to achieve. So, but then it's not only about the radio interface and AI at the radio interface. AI can also help us to create a unifying network experience. We call that UNext, with a nod to Unix, the operating system invented at Bell Labs. Our vision for that network is really that you will have an infrastructure of a multi-cloud, a continuum of cloud compute capability integrated with multiple networks, really networks of networks. On that infrastructure, you then create the different network functions that you need for your 6G service. And it's important to realize that there's multiple actors there. There are the data centers, the different cloud providers, enterprise, CSP, and hyperscalers. Then also different networks. There can be satellite networks, there can be enterprise networks, there can be different access networks and the data center interconnect networks. So there's multiple actors that we need to take there in that network of networks. And then the creation of the applications need to happen also in symbiosis with the applications. So the composition of these services. And therefore, it is a very complex problem where the availability of network data and application data, the knowledge that is embedded in the AI models, really allows for an effective orchestration across these different resources, across the different actors in a unified way. So we talked about the 3 pillars, but there's more to 6G. There is also sustainable 6G, there is secure 6G, and responsible 6G. Let's start with sustainable 6G, has been a theme at this conference very much. There's more than 70% of the power consumption in a network is in the radio access network. So that's an important area of attention for research. And what you ideally want is that the energy follows the traffic load. And you can do that already with microslots, but you can do better. Actually, Shannon has shown that you need to spend the high energy only if you really want a high spectral efficiency. So you can optimize your power even better than linear, the transmit power. You can also, in massive antenna arrays, you can start think of muting segments of your antenna array, and with that, the digital front end, and if you have a scalable baseband processing, also the baseband processing. Then there's further research on the front end itself, on power amplifiers that are integrated with approaches for DAC and ADC that give you further energy efficiencies. So as an example of the importance of research in sustainable 6G. The other one is secure 6G. And here is, I take another part of our new Nokia logo, and what our external design company probably didn't realize, that there's also a quantum bracket symbol in there, by which I remember from college, we notate the quantum states. And you see here a picture of our own quantum research, where we do research on topological qubits. Why do I use that to start talking about 6G security? Well, on one hand, I'm very proud of this type of research that we do. But on the other hand, there was a guy at Bell Labs, Peter Shore. He figured out that actually encrypted code that is deemed safe today can be hacked with quantum computers. So we need quantum safe encryption. But there's more. Also, AI can actually hack encrypted code. So we also need AI-safe systems. AI also that a malicious person can try to behave using AI as a benign user, but hack the system. On the other hand, AI is also a good tool. It can help us detect anomalous behavior and malicious behavior. So there's a new cat and mouse game that is starting to happen. There's also the element of trust. We're using AI models for making critical decisions in our infrastructure. Can we trust the models? And larger, it's basically going to be a zero-trust infrastructure where you have billions of devices, various software components coming from different sources, some maybe even open source, different components, so more interfaces. So there's a huge threat surface. How do you create a trusted service in a zero-trust infrastructures with such concepts as anchors of trust and distributed ledgers, for instance? And then last but not least, also privacy. If you have this multi-actor, multi-stakeholder collaboration, how do you preserve privacy with such concepts as homomorphic computing or differential privacy?
Okay, so AI. The AI is now used so much, so many business, so many applications already. But in the future, we will use it more. And AI is now improving so fast. And we will use AI even in the 6G era, of course. And in the 6G, maybe 6G network will be AI native. If so, we need to rely on the AI more and more. If so, responsible or ethical AI is one of the important challenges to be considered for the 6G. The 6G, our 6G need to be supported. The AI need to be fair to avoid any discrimination or bias. And also AI has to be accountable and transparent for everybody to know the AI behavior anytime. And AI has to preserve the privacy or security, of course. And also has to be reliable, safe. And also AI should minimize the power consumption for sustainable society. And this is a time schedule of the 6G development. And as you know, the variety of the 6G activities has already started all over the world. In the ITU, they approved the time schedule for the IMT30 project. And by 2030, they will complete the specification work in ITU. And also, variety of the 6G research project has already started, including the HEXA-X12, SNS, and the ION, proposed by our parents' company, now global project. And also, we have many regional activities on the 6G. In Japan, the Beyond 5G Promotion Consortium started, and we are aggressively discussing on the 6G topics. And now, it is very important to collaborate between the 6G organizations to take a global unified approach so that we can develop the single global standard. That is a very important point. And also, regarding 3GPP, they did not have any formal activities for the 6G, but many of the stakeholders has already discussed on the time schedule of the 6G in 3GPP. We think that maybe a requirement discussion need to be started from the release 19 timeframe and the release 20 timeframe, feasibility study on the 6G, and the specification work should be release 21 so that we can develop the first 6G specifications by around 2028 so that we can launch our 6G commercial services in around 2030. And also one more thing, and in 2025, there is a very important milestone. We will have the World Expo in Osaka, Japan. And in this event, we intend to exhibit the pre-6G systems so that we can show the future sustainable society in that event. So please come to Japan, Osaka, in 2025.
Okay, we're coming to the end of this keynote, and I hope you start appreciating that a large body of research work has happened. Another case in point is the progress that the HEXA-X project has made, and you've seen this slide before. So if you haven't done so, please visit the booth of HEXA-X. There's 6 tangible demos there on the progress of 6G. So to summarize, what you really should take away is that 6G is coming out of the exploration phase, and we really need to get our act together and get into the systematization phase. Thank you for your attention.
Thank you very much. Thank you. Excellent view on the challenges for research and what comes next research, right, for 6G. Thank you very much. So again, lights in the room, please. And we have time again for a couple of questions. So,
Front.
anyone?
Oh, there.
Sorry. Sorry. Please go to the microphone and identify yourself.
Professor Muhammad Rashid from SAB. I'm working as consultant in SAB, also in Ericsson. I have 2 questions, but first of all, thank you for impressive presentation. First question about the electromagnetic waves. I asked this question many times in this conference, but nobody answered me. Electromagnetic waves have duality nature, waves and particle. Beamforming depends on the constructive interference in the waves. But nobody studied the particle property for the electromagnetic waves. For example, now we are using the terahertz frequency. In the future, maybe we will near from gamma ray frequency. We have radiation pressure. Nobody add this factor in the equations for radiation pressure. The second question, all the antennas now using the copper, gold maybe as a material, but I think if we are using the carbon nanotube for a higher electron mobility, because the electromagnetic waves can generate it by the oscillation of the electron. If we are using the carbon nanotube instead of copper, we have higher speed frequency. Thank you so much.
Thank you. These are interesting questions, really touching on the foundations of the physics, and we should, as a community, look at this. I think the frequency domains that we are envisaging here, I think the particle properties are not yet at play. I think they, as you in your question already hinted, start playing as you get to the higher frequencies. So indeed, terahertz and photonic, that starts making sense, and then there's impulse and things that you can leverage. So I think for the problem space that we look, upper midband and subterahertz, it's maybe an interesting direction that we need to think further. But the particle properties don't really affect that much our way of thinking. I think it's more the wave property. On the carbon nanotubes and so, interesting material science, I think. I think it is not at the maturity level that we should already take it into system designs, but it is an interesting material science that we should watch for sure. Thanks for the question.
Thank you. We have a second question here and the last one because we're already out of time. Thank you.
I'll make it short. Yeah. My name is Fred Bouwing. I'm from Hyro Micro Data Centers. So we develop intelligent edge data centers that look at edge services with AI and the applications on top and try to align that AI. And we are convinced that we need to align it with the network AI as well. And so we look for collaborative opportunities, but it's quite difficult to work with, well, I'm not saying it's quite difficult to work with the large operators, but to be involved with them, because we look from the data center side and not from, I mean, we need the network, but it's not part of our core, let's say, knowledge base. So we need to have that close alignment. It's very difficult to find the right entry point with the large operators. I don't know. Yeah.
Well, you're talking operators, Nakamura, and you want to take a stab at this.
Yeah, okay. So, of course, with DOCOMO is already collaborating with a variety of the partners. Yeah, but yeah, maybe some kind of the difficulty to collaborate and communicate with global partners, foreign partners. But yeah, we have already collaborating with many of the global partners to develop the applications AI solutions to be implemented in our operators make, so-called DOCOMO make. So, of course, yeah, you can contact to me or my colleagues, but of course, we need to develop the win-win relationship. What kind of the monetized win-win relationship can be developed? That's the point, yes.
The monetization is the aspect, of course, because we are not a large data center operator. We have small ones.
Yeah.
So
Yeah.
That should be.
So I understand that you look at the big investments, but we're the small ones. So that's an ecosystem that still needs to grow, I think.
Yeah, and I think in 6G it's important to enable that ecosystem, and we do consider enterprise data centers and CSP far edge also a part of that cloud continuum, and so enabling business models with the players like you are part of the architectural discussion. So let's have a further discussion offline.
Yeah, one
Thanks.
point. Maybe for the future we will deploy the more local edge. Local MEC, yes, not public server MEC. So maybe, yeah, as you said, a small size of the MEC or edge computing will be used for the such kind of the new opportunity of the business. Yes, that's a trend.
Okay, thank you very much. Then thank you once again. So, Nakamura-san.
Yeah, thank you very much.
Thank you very much. Thank you, Peter. Thank you for being again in EuCNC.
Thank you.
Thank you very much. Just two housekeeping things. Don't forget to answer the survey and to vote for the best booth. Enjoy the coffee break. Thank you very much for coming.